You ever sit in a math class and feel like you're trying to read a secret code, but you just weren't given the key? Well, today we're going to fix that. We are going to decode one of the most fundamental languages in all of math, set theory. So let's just dive right in. For a lot of us, it starts right here. You walk into your first university math class, maybe Math 101, and the professor starts throwing these symbols up on the board. They look more like, I don't know, ancient hieroglyphs than anything to do with numbers. And just like that, you feel completely and totally lost. And so you start asking yourself, why is this so hard? Is the logic just way over my head? Am I just not a math person? Look, that feeling is super, super common. But the real answer, it's probably going to surprise you. This quote right here just hits the nail on the head. Most students struggle with first-level math, not because the logic is so difficult, but because they don't speak the language. It's not about being bad at math, it's a language problem. And that language is set theory. Today, our goal is to get you fluent. Okay, so let's start with the absolute basic rules. Seriously, think of this part as learning your ABCs. Once you get these down, you'll see how everything else just starts to click. So, first things first, what is a set? It's really simple. It's just a well-defined collection of distinct things. That's it. Think of it like a noun in this new math language. And just like any language, it's got some grammar. The rules are you always name a set with a capital letter, and all the stuff inside it, it goes between these curly braces. And those things I just mentioned, the objects inside the set, they have a proper name. We call them elements. So every single object in that collection is an element of the set. All right, time for our first symbol. This little guy here kind of looks like a curvy E, right? It literally just means is an element of. So if you see something like 2 in element A, all that's saying in plain English is 2 is inside set A. That's all it is. Simple. So what if you want to say something is not in the set? It's so easy. You just take that same symbol and put a slash through it. That now means is not an element of. The logic is just beautifully simple, isn't it? Okay, so we've got some basic vocabulary down. Now let's look at the two simplest ways you can start writing, your first sentences using sets. So on the one hand, you've got the roster method. I like to call it the list method because, well, that's all it is. You just list every single element. So the set of vowels, you write V equals A, comma E, comma I, comma O, comma U. Easy. Then you have the descriptive method, which is just using words. You'd say, set V is the collection of all vowels. That's great for talking, but for higher level math, we need something way more precise. And yeah, that brings us to this guy, the one that trips everybody up. We're going to call it the scary notation, or set builder notation. I know, it looks intimidating, but I promise you, once we break it down, you'll see it's just a super precise set of instructions. That's all. Okay, let's look at this thing. At first glance, yeah, it's just a jumble of symbols. But I want you to think of it like a recipe for baking a cake, or in this case, for building a set. We're going to translate it piece by piece. This breaks it down perfectly. Let's just read it from left to right. First step, you see that X. That's just a placeholder. Think of it as meaning the set of all the things we're looking for. Then you hit that vertical bar. This is the magic key. It means such that, so everything that comes after this bar is just a rule or a condition. The first rule here tells you the family our X belongs to. In this case, it's a natural number. The second rule is a specific condition. It has to be less than 10. So let's put it all together. That whole scary line of symbols really just translates into this one simple English sentence. Set A is the set of all natural numbers X, such that X is less than 10. It's just a super compact way to give instructions. And what are those numbers? Well, 1, 2, 3, 4, 5, 6, 7, 8, and 9. See? Not so scary after all. Okay, let's do another one real quick. What about this? This notation is basically asking a question. What is the set of all numbers X such that X squared equals 9? Well, what numbers fit that rule? 2 of them, right? 3, and also -3. You see how this works? The notation isn't the math problem. It's just a little puzzle that tells you which things to put in your final list. All right, before we finish up, I've got one pro hack for you. This is one of those simple but really fundamental ideas that once you get it, you'll feel like you really speak the language of sets. And here it is, the pro hack. It all comes down to 2 incredibly simple rules about what makes a set, well, a set. Okay, here they are. Rule number 1. The order of the elements does not matter at all. And rule number 2, repetition is completely ignored. If you see an element listed 100 times, it doesn't matter. A number is either in the set or it's not. You can't have more of something in a set. This example makes it crystal clear. Look at the set on the left, 1, 2, 3. Nice and clean. Now look at the one on the right. It's all jumbled up, and the number 1 is repeated a bunch of times. But in the language of set theory, these two sets are exactly equal. Why? Because we just learned the rules. Order doesn't matter, and we ignore any repeats. So when you boil it down, both sets contain the exact same distinct elements, a 1, a 2, and a 3. So there you have it. You now have the basic tools to read and write the language of set theory, for real. But this leads to a really interesting, kind of weird question. Is it possible to have a set that has nothing in it? A collection of nothing? What would you even call that? And why is that idea one of the most important concepts in all of mathematics? We'll get into all of that